Hello, am I audible?
Yes. Yes, sir.
So, okay. So, Myra, just ask.
A broad pipe having a radius 10 centimeter branches into two pipes of radii 5 centimeter and 3 centimeter. If the velocity of flowing water in the pipe of radius 3 centimeter be 5 centimeter per second, determine the velocities of water in the remaining two pipes given that the rate of discharge through the main branch is 600 pi centimeter cube per second.
We have first a tube which is dividing into two branches like this. Just tell me the data, what is given in the question.
Pipe having radius 10 centimeter branches into two pipes of radii 5 centimeter and 3 centimeter. If the velocity of flowing water in the pipe of radius 3 centimeter be 5 centimeter per second, determine the velocities of water in the remaining two pipes, given that the rate of discharge through the main branch is 605 centimeter cube per second.
Rate of discharge is simply Q, which is equals to area of cross-section times velocity according to equation of continuity. Okay, so this particular quantity will be always constant. So in this part, we can say amount of liquid entering through this main branch must equals to amount of liquid ejecting out through these two arms. So we can say A1V1 equals to A2V2 plus A3V3. Since this first branch through which liquid is entering into this and which is divided into two parts, so total amount of liquid ejecting out will be A1, A2V2, A3V3 must equals to total amount of liquid entering into this main branch. Is it clear?
Yes, sir.
So this particular quantity is basically A1V1, which is given. You can find A3V3 since radius is given and velocity of flowing liquid in this part is also given. So take area A3V3 as pi times r squared and velocity to be 5 centimeter per second. So this is given, this is given. For this part, area will be pi r squared where r is 5 centimeter. So from this you will get V2. Okay.
Yes, sir.
Now, since Q is given, which is rate of flow of liquid, so for first main branch, radius is 10 centimeter. So we may write this area as pi times r square, where r is 10 centimeter. So from this relation, we may find V1 as well. Okay.
Yes, sir.
Any more?
Sir, can you please say what is Q again?
This is a topic which is called equation of continuity, which I
Yeah,
defined earlier.
Yeah, I know that, but then the Q here is what?
Q here is a rate of flow of liquid. Rate of flow of liquid. It means volume of liquid flowing through any particular tube at any instant of time per unit time. So Q is basically volume of liquid flowing divided by time taken. Okay, so this particular expression will be equivalent to A times velocity at that instant. Okay, Rahaf?
Yes.
Samira, any more?
Yes, sir. One more. A wind with speed 40 meter per second blows parallel to the roof of a house. The area of the roof is 250 meter square. Assuming that the pressure inside the house is atmospheric pressure, the force exerted by the wind on the roof and the direction of the force will be.
I defined you this particular concept in upliftment of airplane. On increasing velocity, there will be some decrease in pressure and which result in upliftment of any object. So we can write according to equation of Bernoulli's principle as pressure plus half rho v squared. Let's say we are considering it first inside. Mass equals to pressure outside plus half rho velocity outside squared. Since inside there will be no any movement of air, so this particular term mass equals to 0. Inside pressure is maintained at atmospheric pressure, so this will be 1 atm. Now move this P naught to left side, so you'll get P inside minus P naught mass equals to half rho V naught squared. Now this much amount of pressure difference will be capable of uplifting that roof. So this pressure must equals to force acting per unit area of cross section. Okay.
Yes, sir.
So we may write it as force divided by area of cross section equals to half rho V naught squared. In this part, rho is density of air, V is given at which velocity of or air is flowing. We have to calculate force exerted. Area of that roof is given, that is 250 meters square. Okay. So from this we may find force equals to half rho A V naught square. Okay. So Myra, is it clear?
Yes, sir.
Any more?
No, sir.
Okay. So in last class, I defined you Bernoulli's principle and its various application. Let me define the last part of that chapter. Then we'll start new topic. Taurus Law. It mainly defines velocity of efflux or velocity of liquid ejecting through any or ejecting out from any hole if it is met in a container at some depth h. So we have to calculate velocity of efflux. Let me define you. Suppose you have a container or tank in which a hole is met at this point. Liquid is filled up to this level. Let's say height of this level of liquid from bottom is h, and point at which hole is cut out from this top surface is h. So this remaining height will be h minus h. So this height, small h, must exert some pressure on this particular liquid, due to which through this hole, liquid start emerging out. With some velocity, let's say that velocity is VE, which is called velocity of efflux, for which we have to find its expression. Now, since this particular tank is directly exposed to air, so there will be atmospheric pressure at this point. Similarly, this hole, which is also directly exposed to air, so there will be atmospheric pressure at this point as well. Now, we may consider this particular open cross-sectional area in the form of tube to apply Bernoulli's principle like this. So Myra, is it clear till this part?
Yes, sir.
Rahaf, any doubt?
No, sir.
Okay. Now, since this particular hole is very small, so amount of liquid ejecting through this orifice would be very small enough so that the level of liquid may decrease at very small rate such that we may consider rate of decreasing level of liquid at this open end is approx equals to 0. Is it clear?
Yes, sir.
Consider a tank or open tank in which liquid of density rho is filled up to H. A hole is cut out at depth H below surface. So we may define Bernoulli's principle to get velocity of E flux or VE. So we can write according to Bernoulli's principle, pressure, let's say this end is first end and this particular end is second end. So P1 plus half rho V1 square rho G H1 at this first end must equals to P2 plus half rho V2 square plus rho G H2 at this second end. Now, if you put the values related to each term, what we have assumed in this tank, P1 will be, since this surface is directly exposed to air, so this will be P naught. V1, which is the rate at which level of liquid decrease at this first end, we have just assumed it to 0. So it will be 0. H1 is height of level of liquid from bottom, so it will be capital H, rho G capital H. P2 is also exposed to air, so P naught. Half rho V2 is velocity at which liquid may eject out, so it is called velocity of efflux. And rho G H2, which is height of this particular hole from surface, so it will be H minus small h. Is it clear?
Yes, sir.
Rahaf,
Yes, sir.
is it clear? Or do you have any doubt?
Sir, at my school, they were like, Bernoulli's theorem is like basically the work energy theorem for fluids per unit volume.
Bernoulli's theorem basically defines 3 different terms: sum of pressure, kinetic energy per unit volume, potential energy per unit volume at any instant for the flow of liquid is always constant. That's why I've written for the first part, I've just assumed this top surface, this particular surface to be first part.
Yeah.
So sum of these 3 terms at this must equals to sum of these 3 terms at this point. Okay,
Oh, okay.
just write it down and try to simplify for VE. Samara, try to solve. Samara, you got any answer?
Yes, sir, I got.
Tell me.
Root capital H plus H by rho.
No, just check your calculation. Rahaf, you got any answer?
For the second one, the
For we have to calculate this particular expression for VE. We have to simplify it for this.
is it like P naught plus
Okay, just 1 minute. Let me solve. This P naught and this P naught will cancel out.
yeah.
Now, just move this particular term to left side. So you'll get rho H minus minus plus rho G small h must equals to half rho velocity of efflux square. Is it clear?
Yeah.
So in this part, this term and this term will cancel out. So we're left with rho GH equals to half rho velocity of efflux square. So from this, rho and rho will cancel out. Move this 2 to right side. So you'll get velocity of efflux equals to 2gh root under. So this will be your final expression for velocity of efflux. Samara, is it clear?
Yes, sir.
Okay. Now let me define you what is spatial in this particular expression. Suppose you have a body which is dropped from some height h. So its initial velocity is 0. So on dropping through height h, in or under the effect of gravity, let's say it may assume or acquire some velocity v. So using third equation of motion, we may find v square equals to u square plus 2gh. In this, u is 0. So velocity equals to root under 2gh. Is it clear?
Yes, sir.
You have any doubt?
No, sir.
Now just compare these two expressions. In this part, I've just assumed a body which is free falling under the effect of gravity. So through height h, it may acquire under root 2gh. Similarly, in this part, liquid is falling from this particular level to this particular level, that is height h, and it may have acquired same amount of velocity, that is under root 2gh. So we can conclude liquid behaves as free falling body, so that its velocity and same height, or it may acquire same velocity if falling through same height as if it behaved as free falling. Is it clear?
Yes, sir.
Yes.
So we can conclude from this part, hence it behaves as free falling body under the effect of gravity alone. Now, just see this particular diagram after ejecting out. From this point to this point, it is behaving just like projectile motion, what we did in chapter 4, like horizontal projectile. Is it the same? Samara?
Yes.
So we may define its range, time of flight, and all related term what we did in horizontal projectile. So just consider This is vertical line, horizontal line, and liquid having velocity VE along horizontal. So it may acquire this trajectory to hit at this point. So this horizontal distance from the point of projection to the hitting ground is called range. This is called H minus H. So we have in this part two different types of motion. One is along x-axis and the other is along y-axis. Let me define you. Along x-axis, we have initial velocity as VE. Acceleration along x-axis is 0 since this velocity will be constant. Along y-axis, we don't have any initial velocity, but it is accelerated due to gravity and y. So from this y-axis, let me define you time to fall on the ground. So using second equation of motion, s equals to ut plus half at squared. Vertical distance is h minus h. Initial velocity along y-axis is 0 and acceleration along y-axis is g times t squared. So t will be equals to 2 times h minus h divided by gravity root under. So this will be total time taken by liquid to hit the ground. So we may call it as time of flight. Samira, is it clear?
Yes, sir.
Similarly, for this horizontal or x-axis, using second equation of motion, s is equals to ut plus half at squared. Horizontal displacement is range. Initial velocity along that direction is v, and time taken is time of flight t. So if you put the value of these two terms, root under 2gh for velocity of E flux, time taken is 2 times h minus h divided by gravity root under. So g and g will cancel out, 2 and 2, 4. So taking root, it will be 2 times root under h times h minus h as range. Raha, is it clear?
Yes.
Okay, just write it down to this part.
Done, sir.
Rahaf, you have done?
Yes.
Aisha, do you have any doubt till this part? Okay, you have written?
Yes.
Okay. Now, in this part, you may be asked to find condition for maximum range. At which point a hole should be cut to have maximum range? Sumaira, any guess?
So can you repeat the question?
At which point a hole should be made in this particular tank to have maximum range?
At the top.
Okay. Suppose if you met at the top at this point, so height at that particular case will be 0. So velocity of efflux will be 0. So there will be no any fluid ejecting out from that surface. So range will be 0 in that case. Guess another point you will say at the bottom. Okay. So if you take at the bottom, in that case, time of flight will be 0. So range will also 0 in that case also. So let me define you what will be the condition for maximum range. As we have R equals to range is equals to this part. So whenever you have to calculate maximum or minimum value of a particular function, I define you in mathematical physics to get maximum or minimum value of a particular function, just differentiate it and put it to 0. So if you differentiate this part, you will get h equals to h by 2. It means if hole is cut out at the midpoint of this tank, range will be maximum. So if you put the value of small h to be h by 2, so you'll get R max equals to just h. So just remember these two different points. You don't need to just differentiate this part and try to obtain for this term. Okay. Samira, is it clear?
Yes, sir.
Rahaf, any doubt?
No, sir.
Okay, just write it down.
But sir, like we finished this lesson, fluid mechanics in our school, and like most of the things like you like teaching now, we didn't even like I never heard of it like this in the lesson.
Okay, okay.
Yeah.
This is application of Bernoulli's principle. Okay.
Yeah, Bernoulli's theorem and all we learned.
Bernoulli's in Bernoulli's theorem, in Bernoulli's principle, we may have to define some its application, like upliftment of aeroplane, Magnus effect, Taurus Law, these things.
Yeah. Like we learned velocity trade-off. Wait, no, not velocity trade-off. It was the pressure velocity trade-off. That was
Okay.
just like aeroplane and all,
Okay,
airlift.
okay. Your teacher may have skipped this particular part.
Yeah, maybe because like I never heard of this. So
Okay,
even
no
if
problem, no problem. Okay, you all have written till this part?
Yes, sir.
Aisha, done?
Yes, sir. Done.
Rahab?
yes.
Okay, so this is all about fluid part or mechanical properties of fluid. So let me start new chapter, that is thermal properties of matter. So in this part, first is do you have any idea what do you mean by temperature? Samira, any guess?
Rise in degree is known as.
Rahaf,
Sir, is it like basically change of energy? Like,
change of energy. Okay,
yeah,
in
is it
some
like,
other sense we can say. Yes, Aisha?
It's a measure of the average kinetic energy of the particles in the system.
Okay, let me define you. Suppose you have a body like this. So if you touch it in summer, you feel nothing. But in winter, if you touch it, you may feel cold. It means we measure or we may feel any object related to our body temperature. If the temperature of that particular object is cold with respect to our body temperature, we may feel cold. And similarly, we may feel hot depending upon its temperature. So temperature is nothing but relative with respect to some other reference. In this case, I am just considering all object to be with respect to our body temperature, that is 37 degrees Celsius. So in one sense, you will say temperature is nothing but degree of measure of hotness or coldness of a particular object with respect to some reference. In some other sense, you will say temperature is a physical quantity which is responsible for exchange of heat between any two different objects. In some other sense, or in terms of microscopic concept, you will say temperature is a quantity which defines the randomness of a particular particle, or it may define internal energy of that particular particle, which I will define in thermodynamics. Okay. So in this part, we are considering only macroscopic concept, broad concept. So you may define this temperature as a relative measure with respect to some fixed reference. So let me define you. What do you mean by temperature? The measure of degree of hotness or coldness of a body. So in this part, it is nothing but it is relative term which is defined with respect to some reference. Rahaf, is it clear?
yes.
Now for this measurement of temperature, its SI unit is Kelvin. And to measure this temperature, they will have some instrument, let's say thermometer. So it is measured by thermometer. This thermometer may be of two different types. One is called clinical and the other is called laboratory. Range of this particular clinical thermometer will just measure the human body temperature. So it will be about 36 degrees Celsius to 40 degrees Celsius. For this laboratory thermometer, it is based on melting point of ice and boiling point of water. So it will be based on melting point of ice and boiling point of water. So now let me define you how to formulate formula related to any scale and then how to convert measurement of temperature from one scale to another scale. So for any scale, just remember one thing, T minus LFP divided by UFP minus LFP is always constant for any scale. In this expression, T is temperature on that scale. LFP is lower fixed point, which is also called ice point or melting point of ice, which is equals to 0 degrees Celsius in terms of Celsius. Next is UFP, which is called upper fixed point, which is also called steam point or boiling point of water. So in terms of degrees Celsius, it will be 100 degrees Celsius. Rahaf, is it clear to this part?
Yes.
Now let me define you this formula related to any different scale. So we may write T minus LFP divided by UFP minus LFP. This expression must equals to, let's say first for Kelvin, K minus LFP for Kelvin would be 273. UFP for Kelvin is 373 minus 273 equals to, in terms of Fahrenheit, it will be F minus 32 divided by 212 minus 32. In terms of Celsius, it will be C minus 0 divided by 100 minus 0. In terms of resistance, if platinum wire or any wire is related with temperature, or resistance of those wire is related with temperature, we may find the resistance of those wire at some temperature C, resistance at 0 degrees Celsius, 100 degrees Celsius, 0 degrees Celsius. Similarly, we may define length of mercury column, which is dependent with change in temperature. So length of mercury column at some temperature C, length at 0 degrees Celsius, length at 100 degrees Celsius, length at 0 degrees Celsius, and so on. We may formulate different expression related to this formula only. Samaira, is it clear, or do you have any doubt to this part?
No, sir, no doubt.
Okay, just write it down. Then I'm defining you how to calculate temperature from one term to another term.
Done, sir.
Done, sir.
Rahaf, you have written?
Yes, sir.
Okay. So first question related to this part will be, find temperature at which reading of Kelvin and Fahrenheit is numerically equal. Find temperature at which reading will coincide. First, Kelvin and Fahrenheit. Second, Fahrenheit and Celsius. Let me define you how to approach this part. Just put the value of K and F in this expression as X. So for first part, we may write it as X minus 273 divided by 373 minus 273 equals to X minus 32 divided by 212 minus 32. Just simplify this particular expression to get X. Similarly, in second part, at which numerical value F and C coincides. So relate these two equations and write the value of each part. F equals to Y as C equals to Y. Now, try to simplify this particular expression to find Y. Try to solve these two terms. Samara, you got any answer?
No, sir, doing.
Sir, can you show like how?
Okay. Just 1 minute. Samara, let me solve. We can write x minus 273 divide by 373 minus 273 is 100 equals to x minus 32. 212 minus 32, it will be 180. So this 0 and this 0 will cancel out. Now take cross multiplication. So you'll get 18x minus 18 into 273 equals to 10x minus 320. Now move expression or variable to one side and constant to one side. So it will be 18x minus 10x equals to 18 into 273 minus 320. So 18 minus 10, it will be 8x. 18 into 3, 54. 18 into 7, 126 plus 5, 131. 18 into 2, 36 plus 13, it will be 49 minus 320. So on subtracting, you will get 4 minus 0, 4, 11 minus 2, 9, 8 minus 3, 5, 4. Divide by 8 equals to x. So 8 into 5, 40. 5, 9, 8 into 7, 56, 3, 4, 8 into 4, 32, 2, 5. So at this temperature, Kelvin and Fahrenheit will numerically coincide. Good, Aisha. Samira, any doubt?
No, sir.
Okay. Try to simplify the second part, which is easy. Samara, you done a little mistake. Just check your calculation. Rahaf, you got any answer?
Sir, I'm doing.
Let me simplify. You can write y minus 32 divided by 212 minus 32 as 180 equals to y minus 0 is y divided by 100. So this 0 and this 0 will cancel out. Just cross multiplication. It will be 10y minus 320 equals to 18y. Move this 18y to left side. So you'll get 10y minus 18y equals to plus 320. So it will be minus of 8y equals to 320. So y equals to 320 divided by minus 8. So it will be just minus 40. Samira, is it clear?
Yes, sir.
Rahaf, any doubt?
No, sir.
Okay. Just write it down. You all have written?
Yes, sir.
Aisha, done?
Yes, sir.
Okay. Now, similarly, on the basis of this above concept, there will be a question to formulate formula and then simplify it to get result. Let me define you. Suppose a faulty thermometer reads ice point as 5 degrees Celsius and steam point as 95 degrees Celsius. Find the reading of 60 degrees Celsius on this scale. Let me define you how to approach this part. In this part, we have two different thermometers. One is 40 thermometer, and we have to relate this part with Celsius scale. So just write 40 and Celsius scale. So for this 40 thermometer, F minus lower fixed point, that is ice point, which is 5, upper fixed point 95, lower fixed point 5. Similarly, in terms of Celsius, it will be C minus 0 divided by 100 minus 0, according to the formula. Now equate these two terms. So for this value of C to be 60 degree, you have to calculate the value of F. So put the value of C to be 60 degree and simplify this expression to find F. Is it clear? Samira?
Yes, okay.
Okay, try to solve. Good, Samira. Aisha, you got any answer?
No, sir, I'm doing.
Okay, let me solve. F minus 5 divided by 95 minus 5 will be 90 equals to 60 divided by 100. So move this 90 to the right side. So you'll get F minus 5 equals to 60 into 90 divided by 100. So this 0 and this 0 will cancel out with this part and this part. 9 into 6, it will be 54. Move this 5 to right side. So F will be equals to 54 plus 5. It will be just 59 degree. Rahaf, is it clear?
Yes, sir.
Okay. Rahaf, you have written.
Yeah, sir.
Aisha, done.
Done, sir.
Okay. So this is all about thermometry and how to calculate temperature variation and how to define scale for measuring temperature. Next and most important part of this particular chapter is thermal expansion. Suppose at low temperature, initially at low temperature, particles in a particular solid may be arranged like this, in which separation between them will be small, or you'll say force of attraction between them will be large. So on increasing temperature, or you'll say on high temperature, particle will gain some thermal kinetic energy, or you'll say on increasing temperature, bond gets weakened. So separation between particle increases. So this particular arrangement may get acquire shape like this. So you'll say on heating, solid get expand. Is it clear?
Sir, these are the particles.
Yeah. I'll just consider any particular solid. At low temperature, initially particles are arranged like this, in which separation between them is small along its length or along its breadth. But on increasing temperature, particle will get enough temperature, so its kinetic energy will increases, which increases the separation in between them. Hence, they get expand. So we can say on increasing temperature, thermal kinetic energy, which is related as kinetic energy equals to 3 by 2 kBT. Kb is any constant and T is its temperature. So if you raise the temperature, kinetic energy of particle also increases. Due to this increase of thermal kinetic energy, separation between particles increases. Separation between particle increases, hence solid on heating get expand. Samira, is it clear?
Yes, sir.
So we have to calculate expansion in a particular solid in 3 different ways. First, in terms of length, in which we neglect its width, or we just consider width to be very small as compared to length. Next, in terms of area, in which we consider width of that particular strip to be very small. And third, in terms of volumetric. So let's start first part, that is called linear expansion of solid. Suppose you have a rod having length L naught at some initial temperature T naught. So on raising temperature, its length would increase, let's say to this point at some later temperature T. So length of this particular rod is now L. So difference of length between these two shape is from this point to this point. Let's say this is delta L. Is it clear to this part?
Yes, sir.
Now for this particular quantity, we may define a term which is called alpha, which is called temperature coefficient of linear expansion. Alpha defines at what rate with respect to change in temperature this particular solid or this particular rod is expanding or contracting on increasing or decreasing temperature. So this particular alpha is equals to change in length divided by initial length times change in temperature. This particular term, that is change in length divided by length, we may call it as fractional change in length, and this delta T is change in temperature. So SI unit of this alpha is Kelvin inverse or degree Celsius inverse. Let me define it. It is nothing but the ratio of fractional change in length, that is delta L by L naught, to the change in temperature. Its physical significance is it simply defines at what rate this particular rod would expand or contract on changing temperature. So you can say it defines a rate of increase or decrease in length with respect to change in temperature. Just write it down to this part first, then I'll explain.
So scroll down. Done, sir.
Aisha, you have written?
Yes, Sridhar.
Okay. Now, depending upon this particular relation, we may expand this as alpha equals to delta L divided by L naught times delta T. So just cross multiply it. So it will be alpha L naught delta T equals to delta L. We may write delta L as L minus L naught equals to alpha L naught delta T. Move this L naught to right side. So L will equals to L naught alpha L naught times delta T. Now take out L naught as common. So it will be 1 plus alpha delta T equals to final length L. So this will be our final expression of getting length at any change in temperature delta T. Is it clear?
Yes, sir.
Okay. Let me define you. First, write it down. Then I'm giving you some problem related to this part. Using the above concept, try to find let me give you some hint related to this question. We have initial temperature T naught as 27 degrees Celsius. Length at this temperature is 1 meter. Final length at some temperature later is 101 centimeter. We may write it as 1.01 meter. Alpha is given 2 into 10 to the power minus 4 Kelvin inverse. So we have to calculate temperature at which length would become 101 centimeter. Use the above formula and try to find So Myra, you got any answer?
No, sir, don't.
Just see how to simplify it. Suppose we have alpha equals to delta L by L naught times delta T. So move this delta T to the left side and alpha to right side. So delta T equals to delta L divided by L naught times alpha. Now this delta L is nothing but change in length. So it will be 1.01 minus just 1. So it will be 0.01 meter. So put the value. Divide by initial length 1. Alpha is 2a into 10 to the power minus 4. So if you remove this decimal, you will get 10 to the power minus 2. Delta T is final temperature minus initial temperature. If you move this 10 to the power minus 4 to numerator, it will become plus 4. And we have already 10 to the power minus 2. So on simplifying, you will get 100 divided by 2. So it will be 50. Now move this 27 to right side. So T will be equals to 77 degrees Celsius. So at this temperature, length of this particular rod would become 101 centimeter. Is it clear?
Yes, sir.
Yes.
Okay.
Done, sir.
Aisha, done?
Yes, sir.
Okay. On the basis of this linear expansion, let me define you some concept. Since alpha equals to delta L divided by L naught times delta T. So if you move this delta L by L naught to one side, so you get alpha times delta T. This particular fraction, what is called, I defined this particular part in mechanical properties of solids. Change in shape of any object divided by its original shape. Samira?
Bulk modulus.
No, it was the ratio of volumetric stress divided by volumetric strain. This is the ratio of change in length divided by its original length, or you can say it is ratio of deformed shape to the original shape. So this is called strain. And since this particular strain is due to change in temperature, so we can write it as thermal strain. Is it clear?
Yes, sir.
Similarly, we may define some other term as, according to relation, Young's modulus equals to stress divided by strain. So stress will equals to Young's modulus times strain. Strain we have calculated above, so we may write it as pi alpha delta T equals to thermal stress. Is it clear?
Yes, sir.
And now stress is nothing but force divided by area of cross section. So we may write stress equals to force by area of cross section. So force equals to area of cross section times stress. So it will be Y alpha delta T. Just write it down till this part.
That's it.
Samara, done?
Done, sir.
If temperature coefficient of linear expansion is 2 into 10 to the power minus 4 Kelvin inverse. Find change in temperature so that thermal strain developed will be 2%. Use the above formula and try to simplify. Samara, any problem while solving?
So which formula should we use?
I define you above. What is the relation between thermal strain and alpha? Just this part.
Okay, sir.
In this question, thermal strain is given in terms of percentage. So we may write it as delta L divided by L into 100 is 2. But we have to calculate delta L by L only part. So delta L by L equals to 2 divided by 100, or you may write it as 2 into 10 to the power minus 2. Now use the above formula and try to find delta T. Good, Samaira.
Sir, can you please do it once?
Okay. According to the relation, alpha equals to delta L divided by L naught times delta T. So we have to calculate delta T. So delta T equals to delta L by L times alpha. Now we have this part as well as this part. So delta L by L is 2 into 10 to the power minus 2 divided by alpha, which is 2 into 10 to the power minus 4. So this 2 and this 2 will cancel out. If you move 10 to the power minus 4 to numerator, it will become plus. So 10 to the power minus 2 and 10 to the power plus 4, you will get 10 to the power 2, or that will be 100 degrees Celsius. Aisha, is it clear?
Yes, sir, thank you.
Okay.
Done, sir.
Now, on the basis of this linear expansion, let me define you its application. First application is bimetallic strip. Means two different material or metal get attached to one another to form single. Suppose you have a rod, this, having coefficient of linear expansion alpha 1. Another rod, this, having coefficient of linear expansion alpha 2. Now just consider alpha 1 is greater than alpha 2. So you'll be asked, what will happen if temperature of this particular system is increased and similarly temperature of this particular system is decreased? Samaira, any idea what will happen?
If temperature increases means there'll be more it will expand.
Okay, so will the shape of these particular combination will remain linear or it will get bent?
Linear.
Just see this particular relation. We have alpha 1 greater than alpha 2. This alpha, that is coefficient of linear expansion, simply defines you rate at which it is getting expanding with respect to change in temperature. So since alpha 1 is greater than alpha 2, so there will be more expansion in blue rod as compared to this red one. So blue rod will expand more as compared to red one. So the shape of this particular bimetallic strip would become this. In which this blue one is towards convex side and this red one is towards concave side. Is it clear?
Yes.
So you'll say body having more coefficient of linear expansion will move outward or it will be towards convex side, and the body having lesser coefficient of linear expansion will be towards concave side. Similarly, what will happen when we decrease temperature of this particular system? We are considering this particular part to be initial. And now what will happen if you decrease temperature? Will it be linear or curve?
Curve.
Good. So in which side blue rod will go and towards which side red will go?
Red will go towards a convex side.
Good. Let me define you its reason. Since alpha defines you rate at which it is expanding, similarly, alpha also defines the rate at which it will get contracted. So on changing same amount of temperature or on heating, blue rod will expand more as compared to a red one. Similarly, on decreasing temperature, length of contraction will be more in blue rod as compared to red one. So blue rod will get contracted more, so may acquire this concave side. And since there will be lesser contraction in this red one, so it will go towards convex side. Aisha, is it clear?
Yes, sir.
Okay, just write it down.